Priority queue. A priority queue is a special type of queue in which each element is associated with a priority value, are served on the basis of their priority. That is, higher priority elements are served first. However, if elements with the same priority occur, they are served according to their order in the queue. Assigning priority value. Generally, the value of the element itself is considered for assigning the priority. For example, the element with the highest value is considered the highest priority element. However, in other cases, we can assume the element with the lowest value as the highest priority element. We can also set priorities according to our needs. Difference between priority queue and normal queue. In a queue, the first in first out rule is implemented, whereas, in a priority queue, the values are removed on the basis of priority. The element with the highest priority is removed first. Implementation of priority queue. Priority queue can be implemented using an array, a linked list, a heap data structure, or a binary search tree. Among these data structures, heap data structure provides an efficient implementation of priority queues. Hence, we will be using the heap data structure to implement the priority queue in this tutorial. A max heap is implemented in the following operations. A comparative analysis of different implementations of priority queue is given below. For the linked list, the peek operation has a time complexity of big O of 1, as it simply retrieves the value of the head node. The insert operation has a time complexity of big O of n, as it may require traversing the entire list to find the appropriate position for insertion. The delete operation also has a time complexity of big O of 1, as it involves removing a node from a known position. For the binary heap, the peek operation has a time complexity of big O of 1, as it directly retrieves the value of the root node. Both the insert and delete operations have a time complexity of big O of log n, where n is the number of elements in the heap. These operations involve restructuring the heap to maintain the heap property, which requires traversing the height of the tree. For the binary search tree, similar to the binary heap, the peek operation has a time complexity of big O of 1, as it retrieves the value of the root node. Both the insert and delete operations have a time complexity of big O of log n in the average case, as they involve traversing the height of the tree to find the appropriate position for insertion or deletion. However, in the worst case, these operations can have a time complexity of big O of n if the tree is highly unbalanced. Priority queue operations. Basic operations of a priority queue are inserting, removing, and peeking elements. Before studying the priority queue, please refer to the heap data structure for a better understanding of binary heap, as it is used to implement the priority queue in this article. Inserting an element into the priority queue. Inserting an element into a priority queue max heap is done by the following steps. Insert the new element at the end of the tree. Now, heapify the tree. Algorithm for insertion of an element into priority queue max heap. If there is no node, create a new node. Otherwise, if a node is already present, insert the new node at the end, the last node from left to right. Then, heapify the array. For min heap, the above algorithm is modified so that parent node is always smaller than new node. Deleting an element from the priority queue. Deleting an element from a priority queue max heap is done as follows. Select the element to be deleted. Swap it with the last element. Remove the last element. Now, heapify the tree. Algorithm for deletion of an element in the priority queue max heap. If node to be deleted is a leaf node, remove the node. Otherwise, swap node to be deleted with the last leaf node, then remove node to be deleted. Finally, heapify the array. For min heap, the above algorithm is modified so that the both child nodes are smaller than current node. Peeking from the priority queue. Find maximum or minimum. Peak operation returns the maximum element from max heap or minimum element from min heap without deleting the node. For both max heap and min heap, return root node. Extract maximum or minimum from the priority queue. Extract max returns the node with maximum value after removing it from a max heap, whereas extract min returns the node with minimum value after removing it from min heap. Priority queue applications. Some of the applications of a priority queue are Dijestra's algorithm for implementing stack, for load balancing and interrupt handling in an operating system, for data compression in Huffman code.